The general idea of a series being able to converge is first that the terms must be approaching zero, because if we are adding an infinite number of things, the only way to prevent the sum from being infinite is to have the terms approaching zero. The terms must get smaller in order to balance out the infinite addition of positive values. Now, we have several tests that we've learned so far: the integral test, the direct comparison test. However, the direct comparison test, it was very limited because it required not only finding another series to compare it with and being able to tell the convergence or divergence of that series, but we needed it to specifically be larger than the original series or smaller than the original series based on whether the comparison series converges or diverges. And that made it at times very difficult to use. But there is another way to look at this. We can simply compare the growth rates of, or rather the decay rates of the terms of the series, the growth rate of the sum, to see if the terms are approaching zero at a comparable rate, then the series either both converge or both diverge. So for example, if we were using the direct comparison test, the harmonic series 1 over n is a good comparison series for something like, say, 1 over n minus 1. The reason being that 1 over n is smaller than 1 over n minus 1. And since 1 over n diverges, it then forces the other series to diverge because it's larger. On the other hand, if we had 1 over n plus 1, then the series 1 over n is not a good comparison series because 1 over n plus 1 is smaller. So knowing that the harmonic series diverges and then having a series that is smaller than it, unfortunately, doesn't help us know what's going on with the smaller series. So we have two very similar series here, and for one of them, the harmonic series is a good comparison series, and for the other, it's not. However, the limit comparison test talks about the growth rate or decay rate of the individual terms, thus the growth rate of the sum. And if the growth rates are comparable, then the series are going to do the same things. Because if one of them, the terms shrink fast enough to overcome the infinite sum, and thus provide a finite sum, then that would have to be true for the other, since the terms are dropping to zero at a comparable rate. So the limit comparison test works like this. We're going to have two sequences of terms, and they're both going to be positive sequences, meaning that all of the terms in the sequence are positive. We're then going to look at the limit as n goes to infinity of the ratio of the terms of the sequences. So the limit as n goes to infinity of the corresponding terms of the sequences in ratio to each other. And it doesn't actually matter which one is on the top. Without loss of generality, I'm just putting a sub n on the top. If this limit comes out to be a finite value L, if the limit exists, then that means that the terms of the sequence a sub n and the terms of the sequence b sub n are shrinking at a comparable rate. Or I should say, changing at a comparable rate. And what that means is that if one of them is known to diverge, then the other must also diverge. If one of them is known to converge, then the other must also converge. So by looking at the growth or decay rates of these two sequences, if they share the same growth rate, then the series will either both converge or both diverge. So in this way, we don't have to worry about whether the comparison series is bigger or smaller term by term. We only need to worry about, do they change at a comparable rate? If, on the other hand, the limit as n goes to infinity of a sub n over b sub n is equal to 0, then the reason it's equal to 0 is because the terms of a sub n are not growing as fast as the terms of b sub n. The b sub n terms are growing much more quickly. Or, looking at it the other way, the terms of a sub n are shrinking much more quickly. In any case, the terms for b, the corresponding term of b of n is always bigger. What happens then is that, in this case, the series b sub n has a higher growth rate. Now, this is where we start seeing the similarities to the direct comparison test, because this is only going to help us if we know that b sub n, the series b sub n, converges. This is based on the idea that if the terms of the sequence of b sub n are not shrinking as fast as those for a sub n, then that means the terms for a sub n are, term by term, smaller. And just as with the direct comparison test, if the bigger series converges, it forces the smaller series into convergence. Going the other direction, if the limit as n approaches infinity of a sub n over b sub n is equal to infinity, then in this case, it's because the terms of a sub n have the higher growth rate. What that means is that the series a sub n is larger than the series b sub n. So, like the direct comparison test, if the smaller series b sub n is known to diverge, then it forces the larger series a sub n into divergence as well. As an example, let's consider the two series that I mentioned at the beginning of this video. Let's consider the series 1 over n minus 1. Now this, because of the denominator being n minus 1, we need the series to start at 2. When n is 2, the denominator is 1. When n is 3, the denominator is 2. When n is 4, the denominator is 3, and so on. So we can see that this actually does produce the harmonic series. Therefore, it definitely diverges. What we're going to do now is the limit comparison test with the harmonic series. So the idea here is to take the limit as n goes to infinity of the original series 1 over n minus 1 over the comparison series 1 over n. Now this is a complex fraction, and one way to handle them is to rewrite the division as a multiplication. The numerator multiplied by the reciprocal of the denominator. And this gives us the limit as n approaches infinity of n over n minus 1. Now, without going through all of the algebra necessary to evaluate this limit, we could use L'Hopital's rule. We also could use the idea of multiplying the top and bottom both by 1 over n. We also can just recognize that this is a rational function with the same degree numerator and denominator, and thus, when n approaches infinity, the function approaches the ratio of the lead coefficients, which in this case is 1. This is a unique finite value, a non-zero unique finite value. Therefore, these have a comparable growth rate, as we can see by the fact that they actually produce the same terms. So since we know the harmonic series diverges, then the original series must also diverge. Using the other of the two series that we began with, and this can start at n equals 1, this time the terms of the series are 1 over n plus 1. So when n is 1, we have 1/2. When n is 2, we have 1/3. When n is 3, we have 1/4, and so on. So again, what we see here is the same terms of the harmonic series, except for missing the very first term of 1. So this should pretty clearly diverge as well, since it's all of the same terms. And sure enough, the limit comparison test with the harmonic series will show that. So we again are going to have the limit as n approaches infinity of our original series over our comparison series, where, just like before, we can rewrite this as the fraction in the numerator, times the reciprocal of the fraction in the denominator. And just like before, we get a degree 1 polynomial in the top and a degree 1 polynomial in the bottom. And the fact that this time we have a plus 1 in the denominator, as opposed to the previous one that had a minus 1 in the denominator, those minus and plus 1s are actually irrelevant in terms of evaluating the limit. So remember, we started with the idea that by the direct comparison series, the harmonic series would help with one of these but not the other. In the limit comparison test, the harmonic series helps with both of them. So the limit comparison test is a bit more forgiving than the direct comparison test, and therefore tends to be a bit more useful. Looking at some other examples, let's consider the series 1 over 3 to the n minus n squared. Now, eventually, 3 to the n is going to be larger than n squared. So the 3 to the n is going to eventually control, actually not even all that far out, is going to control what the denominator is actually doing. So a good comparison test for this, a good comparison series, would simply be 1 over 3 to the n. It's a simple series, which will make it easy to work with, and furthermore, it is a geometric series, so that the convergence of it is well known. This is a geometric series with a ratio of 1/3. And if the ratio is smaller than 1 in magnitude, then the series converges. So for the limit comparison test, we will take the original series, the terms of the formula for the term of the original series, over the formula for the term of the comparison series, where, once again, we're going to see this become the numerator fraction multiplied by the reciprocal of the denominator fraction. Now, unfortunately, this is not a rational function because the numerator and denominator are not polynomials, but it is pretty clear that both the numerator and denominator will approach infinity, and that means that we can use L'Hopital's rule. L'Hopital's rule, again, states that we can do the limit of the derivative of the numerator over the derivative of the denominator. Now, working through this, we will see what happens, but the basic idea is that the derivative of an exponential function is still exponential. But in the denominator, we also have a polynomial term, and that polynomial term will reduce in degree until eventually it becomes constant and then 0. So what we have here is the limit as n approaches infinity of 3 to the n times the natural log of the base. And the denominator, we have 3 to the n times the natural log of the base minus 2n. Now this will, of course, still approach infinity in the top and bottom. So we can do it again. The derivative of the top will again be 3 to the n times another natural log of 3. So we end up with 3 to the n times the natural log of 3 squared. We will get that same thing in the denominator, but this time the constant term the linear term reduces to a constant term. Now this once again still approaches infinity in top and bottom, but by doing it one more time, that constant term will drop to a 0. So we will again have 3 to the n times the natural log of 3, this time cubed. We'll pick up another factor of that. And the denominator, since the derivative of the 2 is 0, we actually end up with the same expression in the top and bottom. So what we end up with here is the limit as n goes to infinity of 1, which of course is just 1. This is a unique finite value, and thus, since the comparison series is known to converge, we can thus conclude that since they have comparable growth rates, that the original series converges also.